Hey there, welcome to the first part of this tutorial in which we are going to estimate and approximate pi using different approaches. Before we proceed any further, let's just very briefly talk about pi itself. So pi, as you know it, is a mathematical constant and is equal to the ratio of a given circle's circumference to its diameter. Now, pi is almost always rounded to 3.14, but it's basically a never-ending decimal, and there have been many attempts in trying to calculating its digits, and that's exactly what we are going to also do today. In this part of the tutorial, we are going to estimate pi using two approaches, namely Monte Carlo estimation and also the Leibniz formula. Let's begin with the first one. Let's assume that we have a circle of radius r which is inscribed in a square. Therefore, this means that the sides of this square will be equal to 2 times r. Using this information, we can compute the areas of the square and the circle and also compute the ratio between the two, which will be equal to pi over 4. And this is already a nice formula to approximate pi with. We only need to find a good representation for the areas of the circle and the square. One way to do that would be to generate random points and then check whether these points fall inside the circle or are in the square. Let's say that we have a circle of radius 1 which is centered at 0 and 0. And then we just randomly generate points with x and y coordinates between 0 and 1. And because all of these generated points would actually be inside the square, we can say that the total number of generated points would act as a representation for the area of the square, and all of those points that actually do fall inside the circle will act as its area. So to check whether a point is inside the circle or not, we will just compute its distance to the center of the circle, and if the distance of the point to the center of the circle is less than the radius of the circle, then we would say that this point lies actually inside the circle. And using that, or using these two representations, we can basically now compute and approximate pi. We can now code it in Python. I have already imported the libraries that we need, and we can directly start to write the function. It takes in just one input n, the total number of points that we need to generate. Let's now begin by initializing a variable for the total number of points in the circle. We then need to generate points, n points, and each point contains x and y coordinates that lie between 0 and 1. Then we need to compute the points, this generated points distance from the circle, or basically the center of the circle, and if this distance is less than or equal to the radius of the circle, which in our example is 1, then we would say that this number lies inside the circle. And at the end, we are going to just use the computed values to return our approximation for pi. Let's test our function for 1 million generated points. Let's also print out pi. And as you can see, after 1 million generated points, our approximation is only accurate to 2 to 3 decimal points, which shows that this Monte Carlo approach is definitely not an efficient and also not a suitable approach for pi estimation. Alright, let's now check how Leibniz formula will perform when it comes to estimating pi. This formula was proposed by Gottfried Wilhelm Leibniz and is basically derived from the Taylor series of the arctangent function. You can check its proof later. It's kind of interesting. Now, if you see, the right hand side of this formula contains an alternating series which we can represent using this summation. Now here we can see that the signs are changing between each two terms, and also we can see that the denominator is basically the set of all odd numbers. So our final estimation for pi will be made using this formula. Let's now implement it in Python. I have used the decimal library, which allows for a much more accurate representation of the decimals. Let's begin by again defining a function which takes as input just one variable k, which is going to be the total number of terms that we are going to generate from this series. Let's set the precision. I'm going to set it to 1000 digits. Then I need a starting value. It's going to be 1 based on the first term of the series. Then I need to do the summation. So I'm going to loop k times. And I'm going to compute the numerator and the denominator separately. So in numerator, we are going to basically compute the sign, and then in the denominator, as already mentioned, it's going to be basically the set of all odd numbers, and then we just update our estimate for pi. And at the end, we return our computed estimate for pi. Great. Let's test our function by generating the first 1 million terms of this sequence. We can also compare it with the actual value of pi. And because this decimal is going to have 1000 digits, let me convert it to a string so that I can only show the first 20 characters. And as you can see, after generating 1 million terms, our estimation for pi is only accurate to 5 decimal points, which still shows that also this second approach, the Leibniz formula, converges very slowly to the actual value of pi. In the second part of this tutorial, however, we are going to work with some approaches which converge to the actual value of pi much more faster. Therefore, stay tuned in. I'm going to again post the codes on my website and share the link to that post in the captions of this video. Thanks a lot for watching, and see you in my next tutorial.